So in this video, I'm going to summarize the application of Newton's forces. So in previous chapters, we talked about the Newton's first law, his second law, and third law. In this chapter, we basically go over how to apply it to different scenarios. And so, like I said, this is just a summary. So to summarize Newton's first law, which is pretty important, which talks about the sum of the forces equals zero. Okay, so this is the first law. So this means all the forces on an object, they have to be balanced. And if they're balanced, that means there's no acceleration. Okay, so the first law basically means there's no acceleration, right? So if I were to draw like a free body diagram of this, it would look like something like there is maybe a normal force going up, the weight going down, and then maybe some sort of like tension, like a rope or something that's pulling to the right. Okay, so because now the forces are balanced in the vertical direction, so there is no acceleration vertically, but there is an acceleration to the right. Why? Because the forces are imbalanced. Okay, so there is no acceleration. So the first law is actually correct for this direction, but it's not for the other direction. Okay, so this here is imbalanced. So let's imagine there was also some frictional force here, due to a kinetic friction. Okay, so if we did that, and if the kinetic friction and the tension were the same, then this object would be totally balanced in all axes, and therefore it would have no acceleration, which is what Newton's law basically says. It says if the forces are balanced, there's no acceleration, which is pretty obvious. Okay, and then the second law basically means, what if the forces are not balanced or imbalanced? So then the sum of the forces is equal to mass times acceleration. Okay, so in this case, you do have an acceleration. So once again, you could have this. Actually, let me go back. You could have this. Once again, you could have the normal force, weight, and maybe some sort of tension here, right? And so because these forces, let me actually make this right here. So these forces are balanced. These forces are balanced, but this is not balanced. This is not balanced, okay? So because this right here, these forces are imbalanced, that means we're going to do F equals ma. And that means there is an acceleration. So the forces are imbalanced, there is an acceleration. The forces are balanced, therefore there's no acceleration. And of course, lastly, the third law, which says forces act. If an object acts upon something, then the other object can act back on it. So meaning, if you're like a person, let's say there's a person here. All right, and this person is standing on the floor. The person is pushing down on the floor with some weight. Well, the floor is also pushing back with some force. Okay, we usually call that the normal force. So something is pushing down, and then another force is pushing back up, and so that's the third law. Okay, equal and opposite forces. So something is pushing down in some force, so there's something pushing back up in the opposite direction. Okay, so you use these three forces. You use these three laws: the first law, the second law, and the third law, to solve these physics problems. Okay, let's talk about some different types of forces that you may encounter. One, and we talked about this. This is the normal force. This is, like I said, if you have someone and they're standing on the floor, the normal force is what pushes them up. Or maybe they're leaning against a wall. So maybe there's like a wall here, and this is a person, and they're like leaning on the wall like this. Well, the wall is going to push up. Okay, so the normal force doesn't have to be like horizontal like this. It could be at an angle, but it's just pushing up like this. Okay, so that's a normal force. The other one, of course, is friction, the frictional force. Now, the friction actually, how friction works is friction is actually just so. Okay, so let me talk about this. So let's imagine two scenarios here. There is a box. Let's say there's a box here, and there's some sort of force trying to pull it this way. Let's say some sort of pulling. Okay, someone's pulling it with a force, obviously. And then let's say here, then let's say in both cases someone's trying to pull it. Okay, so in the opposite direction we have what's called friction, the friction force. Okay, so in one case here, let's say this first case, the box is not moving. It's not moving. And in this case here, it is moving. So it's not moving, it is moving. So if it's not moving, what does that mean? That means the sum of the forces is 0. It's not, there's no acceleration, okay? And then here in the moving, the sum of the forces equals ma, meaning it is moving, okay? So if it's not moving, then we're dealing with what's called static friction. It's called Fs, or static friction. And if it is moving, we call that kinetic friction. We call that kinetic. Static meaning, of course, not moving. Kinetic means it's moving. So how do you compute static friction? Well, there's a coefficient, and it's usually called like mu. So like mu sub s, and it's normally like 0.4 or something like that. Okay, this is just a value. Okay, it doesn't have a unit. It's just a unitless value. It's like 0.4. So what you do is you take this. So it's mu sub s, your static friction, times whatever your normal force is. So you have to figure out what's your normal force, multiply it times this value here, this coefficient of static friction, and that will give you your force. That'll give you your actual force, because the Newton here, because this is a force, so this is a force, and this is a force. So this is just a number, right? This is just a number. There's no unit associated with it, okay? So just some number times a force gives you a force, okay? And yeah, so the same thing over here. This is mu sub k times normal, and then mu sub k is normally smaller than mu sub s, right? So if mu sub s is like 0.4, maybe this is 0.3, it's less. So what this means is that the friction when you're not moving is stronger than the friction when you are moving. And this makes sense, right? If you have like a box and you're trying to pull it, and then before it pulls, it's like hard to pull it. But then after you start pulling it, it's easier to pull once it gets moving. That's because you're dealing with kinetic friction instead of static friction. And kinetic friction is less than static, okay? So that's why it's easier to keep something moving once it's already moving than initially getting it going. So one interesting thing about static friction is that it's a maximum value. Meaning, let's say I have a box here, okay, and let's say someone's pulling it, okay, and then let's say my static coefficient of friction is like 0 point something, whatever, and then so you say Fs is equal to 4 times your normal force. And so let's just give an example. Let's say it's 300 newtons. Okay, let's say it's 300 newtons, just as an example. If you do this calculation, so that means there's 300 newtons here. Now the thing about this is that's the maximum it could be. That's the maximum that force could be. So what happens here is when you pull, if you pull, I'm just going to show this down here. If you pull with 1 Newton of force, then on the other side, due to friction, you're also going to get 1 Newton. If you pull with 2 newtons, it's going to be 2 newtons. If you pull with 3 newtons, it's going to counteract with 3 newtons. Okay. Now you might be thinking to yourself, yeah, but I thought you said it was 300. So isn't this 300? Well, that wouldn't make sense. Imagine you're pulling a box just a little bit. You're pulling a box a little bit. If this were 300 newtons and this were 3, that means you would have massive acceleration in this direction. So imagine that. If you're pulling the box a little bit, is it going to start accelerating quickly in the other direction? No, that doesn't make any sense. So that's why when you pull, let's for example at 1 Newton, its opposite is going to also be 1 Newton. So it's gonna keep you from pulling it with a force of 1 Newton. So this is basically it's going to mirror you. If you pull at 1, it's going to pull at 1. If you pull at 3, it's going to pull at 3. Okay, but up to a maximum of 300. But once you go 301, once you do 301 newtons, remember its maximum is 300. Now these forces are now imbalanced, and now you're going to start accelerating this way. Now you're going to start accelerating, and then once you start moving, then you start dealing with kinetic friction. So basically, you deal with static friction up until the maximum. In this case here, 300. In this case, 300 newtons. But once you've exceeded the maximum static friction, then you're going to start moving, and then once you start moving, you've transitioned from static friction to kinetic friction. Okay, so anyway, so that's a little bit about friction. Of course, we have weight, which is the force, which is just your mass times the force of gravity. Okay, and then there's another force. I mean, there are a lot of forces out there, but another typical one you'll see in physics is the tension force. The tension force. The tension is like there's a box here, and there's a box here. Maybe someone's pulling it, but there's a rope. There's a rope between these two boxes, and so there's tension on that rope. Right? There's tension. Tension's here. Okay. Yes. So that's it. So just in recap, we talked about the normal force. Normal. We talked about friction, both static and kinetic. And then we talked about weight. And then we talked about the tension. Obviously, there are other forces. This is just the ones you'll like traditionally see in like an introductory physics workbook or something. Let's talk about axes. So, if you do something like this, you have a box here and someone's pulling it, you're going to do a free body diagram. You're like, okay, here's the box, here's the normal force, here's the weight, blah, 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 here's this. But what happens if this box is at an angle like this? So now you have a problem. You're like, okay, the weight is going down like this. The normal force is going like this. Maybe someone's pulling it up. Maybe there's friction in this direction. And so it's not that it's impossible, but now you just have you have to figure out, okay, right? What's this angle here? Maybe what's this angle here? What's this angle here? And you have to do like, okay, so I'm here, I got to figure this out. Well, this is, something times the sine, something times the cosine, et cetera, et cetera. It's not impossible. It just makes it a little bit trickier. So what you could do instead is you could look at this guy like this in your box and say, okay, I'm actually going to, instead of this being my x-axis and this being my y-axis, is you can say, this is my y-axis, and this is my x-axis. This is my x-axis. And now, if you turn it, everything is straight. Now everything is straight. Well, actually, everything is straight except for weight. So if you did this, and then like drew it straight, so you took this, but you drew it straight. So it's still this. I'm just redrawing it. Okay. So then you have your box here, and then you would have, let's say someone pulling it. This is the normal force. This is called the pulling. This is like the normal force, and then maybe the friction is this way. Maybe it's static. Maybe it's kinetic. But weight, of course, is not straight down. Weight would actually be over here. Weight would actually be over here. So, but versus this one here. Let's use this one. In this case here, there's 3 forces that you have to deal with that are at an angle, and then one's normal. Here, 3 forces are straight, and only one's at an angle. So it just makes the math just a little easier to do. Once again, you can do it either way, but if you just change your axis a little bit, then it can make the problem just quicker to solve. But you have to remember, when you're changing your axes, you can make your x-axis whatever you want. But just but just when you put your y in, make sure it's at 90 degrees, or what's called orthogonal to it, or 90 degrees. Okay, you can't have it like x like this and then y like that. So it has to be at 90 degrees to it. So wherever you put it at, it's cool. Just make sure the other one is 90 degrees to it. Okay, and then lastly, I want to talk about circles. So this is a recap, like I mentioned. It's circular motion. Circular motion. Okay, got it. All right, so here we have a circle, right? And so if you were to be right here and you were to go all the way around it, that's called the circumference, right? Circumference. Circumference is pi times the diameter. So whatever the diameter is, which is this right here, which is d, if you do essentially 3 of those, or 3.14, we'll just say just 3. If you do 3 diameters around this circle, 3 diameters is the circumference, or 3.14, okay? So, and that's true of any circle. It could be a super tiny circle to a massive circle. It doesn't really matter. All circles are the same. So, but you could change pi to, or d into 2 pi r, okay? We're here. This is like here. This is your radius. Instead of, so I'm saying d just got decomposed into 2 and r, and then pi we left alone. So c is the total distance in meters. Okay, that's the total distance in meters. Now velocity, as you may remember, is distance over time. And so here our distance is what? Our circumference, and time is t. And then circumference is just 2 pi r, and so that over t. And so this is velocity, 2 pi r over t. Now, if you want to know what the acceleration is, now this is not linear acceleration, so normally what you do is you take your velocity and then take the derivative of that to find the acceleration. You know, dv dt is equal to a, is equal to your acceleration. That's not what it is when you're doing circles, okay? That's linear motion. In circles, it's a little bit trickier to find, but what it is actually v squared over r, okay? And so to view these things, here's my circle, and here's someone that's moving, and let's say they're moving in this direction, okay, here. So the velocity looks like this. The velocity vector is tangential to the circle, and the acceleration vector is actually towards the center. It's actually towards the center. And this is called acceleration radial. It's the radial acceleration, okay? And that always points toward the center. Now, there is another acceleration. Acceleration is a vector, and so there is another component to it, and it's also tangential to the velocity. So it's called acceleration tangential. So it goes in this direction. Now, if the velocity is constant, meaning you're going, say, 3 meters per second, all the way around 3 meters per second, then the tangential acceleration is 0. It's 0. It's nothing. So then the entire vector is just going down. It's just going down. But if your velocity is changing, like it's 3, then it's 4, then it's 5, then it's 6, or whatever, then the tangential acceleration is going to be a component, and so you'll see it get bigger or whatever. And so if you want to find the total acceleration, obviously you take your tangential acceleration and your radial acceleration, and you put those together. You add them up to get your overall acceleration vector. But if the person going in a circle is moving at a constant velocity, then all you have is just this radial acceleration, and you don't have a tangential one. Okay. The other thing I want to mention is, so velocity basically is meters per second, right? 2 pi r. This is in meters. Time is in seconds. Okay, so your velocity is in meters per second. But what if you want to do a velocity that's not in meters per second? What if you want to look at it as in rotations? Like, how many times am I rotating? So that's like your frequency. So your frequency is in like revolutions per some unit time. For example, let's say seconds. So you could say I went 3 revolutions. It spun around 3 times in 1 second. It spun around 3 times in 1 second. Now the inverse of this, frequency, is time. So time is the inverse of frequency. So time, an example of time would be in 5 seconds, I made 1 revolution. Okay, so it just depends on how you want to view the problem. You could say like, oh, I want to know how many revolutions I'm doing per second, or I want to know how many seconds does it take me to do one revolution. So time and frequency are inverse to each other. And yes, the other thing I want to talk about is, so let's go back to forces. So obviously this is, we're dealing with Newton's laws. So if you're looking at, let's say, some sort of spinning thing, let's say a race car or something like that, and it's going in a circle, right? Some sort of car, right? And it's moving in a circle. And you want to look at the forces on this car relative to Earth, right? Relative to Earth. Okay, so Earth is, how we usually use it is what's called an inertial reference frame. Inertial means non-accelerating. So I'm going to compare the movement of this car, to Earth, because Earth is an inertial reference frame. And so if you want to do Newton's first or second laws, you have to compare it against an inertial reference frame, which is Earth. So this car is moving, right? He's accelerating towards the center. So if you look at the free body diagram of this is the car. And then, there's maybe some normal force, maybe there's some weight force, but there is an acceleration, radial, that's pointing towards the center of the circle, which is here, pointing towards the center of the circle. And so this is Newton's second law, right? F equals ma. The forces are, or the sum of the forces are imbalanced. You can see that here because the acceleration is not balanced. See that? It's not balanced, therefore it's accelerating. It's accelerating, quote unquote, towards the center. I mean, it looks like, how's it accelerating towards the center? That's just where the vector is pointing at, okay? It just means this person is moving in a circular motion. So we use Newton's second law for this. This is his second law. Okay? But what if you were to compare, here's the circle again, and here's this. But what if you were inside the car? Imagine you're inside the car, like looking at a person, and you want to do a force diagram of that, or free body diagram of that. So remember, you're inside the car and you're comparing it to the car. So you're inside the car and you're comparing, let's say, a person to the car. The problem is that the car is moving, right? So if you're comparing this, let's say you're comparing a person in the car, let's say that, to the actual car itself. Let me draw a car. The actual car itself looks like this. Well, the car is moving. So the car is not in an inertial reference frame. So you can't do that. Well, you can, but you have to trick it. You have to trick it somehow. And so what would happen is, because you can't normally do this, because the car is moving, you can't compare the person to the car, because like I said, the car is accelerating. Because you'd agree, right? The person, if you're inside the car, if you're looking at the person is not moving, right? So let's say the person here, this is the person here. He still has there's a normal force pushing, maybe the seats are pushing up on him. He has his weight in the car. But because he's in the car is still accelerating radially like this, okay? The car is still doing that. And so you'd look at this diagram here and go, well, it looks like the person's accelerating, but you're looking at him and going, he doesn't look like he's moving at all. So what you need to do is you need to add a fake force. Okay, so we're going to put this over here. We'll just make it red. And this is called a fake or a pseudo force. Yes, a pseudo force. And we call this, so towards the center, this is actually called centripetal acceleration, and this fake force is called centrifugal. Centrifugal. Centripetal means center seeking. It's seeking the center, and then I'm not actually sure what centrifugal means, but it's the opposite of centripetal. Okay, so you put this pseudo force here, and so therefore, you have the sum of the forces equals 0 because he's not accelerating, right? Everything is equal. Therefore, because if you're inside the car and you're looking at someone, you go, this person's not moving at all. And so this is how you can reconcile that. by being in a car that's moving in a circle. You have to add the pseudo force. Once you do that, you go, yeah, okay, so now all the forces are balanced and he's not moving, which is correct. But if you compare it to Earth, which is here, if you compare the car or the person, it doesn't really matter, to Earth, then yeah, this person is accelerating around in a circle, and this shows it. Okay, so we use Newton's second law here, Newton's first law here, but the reason we're going to use Newton's first law is because we're comparing him to the car, but we have to add in this pseudo force. Anyway, that's it. Hope you enjoyed the summary.